Hello everyone, my name is Bjarki and I'm a security engineer at Google, where I work on web framework security. Today, I'm going to show you how you can eliminate cross-site scripting vulnerabilities from your Angular application by adopting a new web platform security mechanism called trusted types. Let's start with a little bit of background. Google's VRP is a bug bounty program that pays external security researchers for reporting vulnerabilities. Looking at the data from 2018 and the total payouts by vulnerability class, we can see that cross-site scripting accounts for more than a third of the entire budget. And considering that almost half the budget isn't even on web-related issues, we can see that XSS is by far the most expensive type of web vulnerability. And this graph looks largely the same even today, as well as if you look at other bug bounty programs. Cross-site scripting vulnerabilities occur when a web application passes user input, which hasn't been escaped or sanitized, into an HTML or script context that the browser then interprets and executes. This can be serious, as an attacker may be able to leverage this to leak sensitive data from users or perform actions on their behalf. This can happen both because of unsafe server-side and client-side rendering. Client-side, or DOM-based XSS, which we are going to focus on, occurs when the application passes user input to one of the dangerous DOM APIs, which we call injection sinks. On the right, you can see some examples of injection sinks. Eval is probably the most recognized one, but assigning to inner.html or script.source are other good examples, and will cause XSS if passed untrusted user input. There have been a number of attempts at mitigating DOM-based XSS, including content security policies, static code analysis, and XSS detection in browsers. While most of these help considerably, as we saw on the previous slide, XSS is still a huge threat. Expanding a bit on content security policies, they allow you to restrict which scripts are allowed to run on your page. They are configured by having your web server send an HTTP header. For example, a content security policy header with a value of script source example.com will make the browser block execution of any scripts that are not loaded over HTTPS from example.com. This ensures that only scripts that you trust are executed on your page. While a good CSP policy may limit or even block impact from DOM XSS in your application, it does not address the root cause of these vulnerabilities, which are unsafe uses of injection sinks, and indeed, attackers may still be able to deface your website or use it for phishing attacks. Luckily, Angular does a great job of limiting direct interaction with injection sinks. It provides a templating language that ensures that all interpolated user input is escaped or sanitized before rendering. If you need to bypass sanitization, you must explicitly call one of the bypass security trust functions, which marks the value as safe for injection into a specific context. But even if a secure web framework such as Angular is used, there are still many opportunities for direct DOM interaction that could lead to XSS. For example, there is nothing that forces a developer to use Angular's templating language, so they may still call out to the DOM directly. And in some cases, this may even be necessary. External JavaScript libraries that the application depends on are also a common source of XSS vulnerabilities, as they frequently perform direct DOM interaction. And both of these points are especially true in enterprise-scale applications, where there is often little oversight over what code gets checked in. This brings us to the main subject, which is trusted types. Trusted types is a new web browser API that allows you to completely block write access to injection sinks. They are a CSP feature and are configured by serving a CSP header with required trusted types for script. When enabled, any attempt at using an injection sink will be blocked by the browser, throwing an exception, also known as a trusted types violation. Angular has recently been made compatible with trusted types, meaning that using Angular and its templating language will not cause any violations. When running your Angular application locally, you can enable trusted types by adding the CSP header to angular.json. You can verify that it works by opening the developer console in your application and executing eval on a plain string. Enabling trusted types makes an application very secure, but it can also break its functionality. So before rolling this out to production, we first need to identify the trusted types violations and fix them. There are a few different ways to identify trusted types violations. The simplest way is to run ngserve and open the application in a browser. Trusted types violations will surface as exceptions in the developer console and contain a stack trace. Enabling trusted types in angular.json will also cause trusted types to be enforced in end-to-end tests. Running ng e2e is a good source of violations if the tests are comprehensive. It is also possible to use static code analysis. We've developed a tool called tsec that looks for trusted types violations in TypeScript code. Finally, you can use a feature of CSP known as report-only mode, which allows you to collect and analyze CSP reports containing trusted types violations from actual users without causing production breakage. This is a good practice before deploying any CSP feature. Now, when you've identified usage of an injection sink that is causing a trusted types violation, you need to refactor that code in a way that does not cause a violation. First and foremost, you should be using Angular's templating language whenever possible. Otherwise, here are some common examples of violations and save alternatives. If you're assigning plain text to inner HTML, you can assign the text to text content instead. If you're constructing some simple inline HTML, you can use save DOM APIs instead. For example, document.createElement, setAttribute, text content, and append child. If you're creating inline event handlers using strings, you should be using add event listener or Angular's event bindings instead. If you're creating web workers and you're using Webpack, you can use import.meta.url to instruct Webpack to inline the worker script in a way that is compatible with trusted types. These are some common examples, but sometimes there is simply no safe alternative. As a last resort, trusted types provides a mechanism known as trusted types policies. These policies allow the application to produce values that are safe for use in specific injection sinks without causing a trusted types violation. Sinks require one of three different types of values depending on the nature of the sink. Either trusted HTML, for example when assigning to inner HTML, trusted script, for example when calling eval, or trusted script URL, for example when creating a worker. Policies are simple JavaScript objects defined by the application. On the right is an example of an application that wants to assign potentially untrusted user input to inner HTML in a safe way. It starts by defining a trusted types policy using the trustedtypes.createPolicy API and giving it a name of sanitize-html. The createHTML function defines how unsafe user input should be transformed or validated to ensure that the resulting HTML is trusted. In this case, the DOM purify library is used to sanitize the HTML. The application can then pass untrusted HTML to the policy's createHTML function, which sanitizes the HTML and returns a trusted HTML value. This value can then be assigned to inner HTML without causing a trusted types violation. In this way, trusted types forces any security sensitive code into trusted types policies. And as a result, these policies must be scrutinized for security. Once all the violations have been fixed, trusted types can be enabled in production. Going forward, we must also ensure that no new trusted types violations appear, as that may break the application. The approach is similar to how we originally identified violations. By enabling trusted types in Angular.json, trusted types will be enabled in development mode. Developers should thus catch any new violations when they are developing a feature. The same applies for end-to-end tests, which should be run as part of your CI pipeline. tsec, our static code analysis tool, can be added as a pre-submit check to your code repository. And in the unlikely case any violations make it into production, you will be notified through CSP reports. One final feature of trusted types that I will want to tell you about is restricting policy creation. This is useful as when you rolled out trusted types policies will remain as the only place where security-sensitive code lives in your application. Policy creation can be restricted by explicitly listing the names of the allowed policies in the Trusted Types directive in your CSP header. In the example on the slide, only the two policies named Sanitize HTML and Angular are allowed. Trying to create a policy with any other name or using the same name more than once will result in a Trusted Types violation. Restricting policy creation gives you even stronger guarantees about the security of your application, and is especially useful in enterprise-scale applications where you may not want developers to create arbitrary Trusted Types policies. Angular itself may create a number of Trusted Types policies, which you can either allow or block using the Trusted Types directive. The Angular and Angular bundler policies are required for basic Angular functionality and are always safe to allow. The Angular unsafe bypass policy is created when any of the bypass security trust functions are called. Depending on whether you allow this policy, you can control whether you want to allow calls to bypass security trust in your application. Angular unsafe JIT is required if you need to use Angular's just-in-time compilation, but using ahead-of-time compilation is strongly encouraged, not only for security, but also for performance reasons. Finally, if you want to use the Angular DevTools while developing your application, you need to allow the Angular DevTools policy, but make sure you only do this locally. Wrapping up, these are the steps you need in order to deploy trusted types. You start by enabling trusted types in report-only mode. You look for trusted types violations, either locally by navigating around your application, or by looking at CSP reports from users. You fix these violations by refactoring code to use safe DOM APIs, using trusted types policies as a last resort. When you're confident you've fixed all trusted types violations, drop the report-only mode and start enforcing trusted types. Finally, you can rely on end-to-end tests and continuous integration to prevent any new violations. To get an idea of how effective trusted types are, we analyzed DOM-based XSS reports from last year's Google VRP program and found that at least 61% of the reported vulnerabilities would have been mitigated by trusted types. And note that this only includes vulnerabilities that were already missed by Google's static code analysis pipeline and security reviews, which is pretty impressive. We've seen how trusted types forces you to use safe APIs and move security-sensitive code into trusted types policies that can be reviewed in isolation. Even in browsers that do not support trusted types, this still increases the security of your application considerably. But trusted types gives you more than that. I was recently playing around with one of my Angular applications when I ran into a trusted types violation. I thought to myself, oh no, I must have forgotten to refactor some insecure code in my application. But after digging into the stack trace, I noticed that the violation was coming from inside the Angular framework. I was using internationalization in my Angular application, and it turned out that in certain scenarios, Angular was not escaping user input that went through the i89 pipeline. I had discovered a cross-site scripting vulnerability in Angular itself, but because I was enforcing trusted types, my application was immune to the vulnerability, at least in browsers that support trusted types. And the same principle applies to obscure but potentially dangerous code paths in both your application and in third-party dependencies. They're simply blocked. So that's it. Thank you for listening, and I hope I've inspired you to give trusted types a try in your Angular application.